As I said, I'm Glenn Magelssen. First of all, before I start, I'm interested in knowing background. How many of you have a scientific background? Raise your hand. Quite a number of you. Okay. This will be fun. So, I started my career at the University of Colorado in solar physics. I studied a phenomenon called the type 3 burst. Type 3 burst is an explosion from a solar flare, creates high energy electrons. Those electrons propagate from the sun to the earth. Measurements are made in between the sun and the earth and near the earth of what that density looks like and what the energy looks like. In addition to that, those electrons create a radiation all the way from the sun to the earth. And so that's what my thesis was about, was developing a model that predicted that kind of behavior. From there I went to the University of Wisconsin, changed fields. As I was telling Wes, what I was interested in was getting to a field more practical. Not sure it was practical. I started my career in inertial fusion at the University of Wisconsin. I developed a radiation hydrocode there. This is back in 1976 and 77. From there, I went to Argonne National Laboratory, continued the code development, adding ion beam physics. At Argonne, I was involved in heavy ion fusion. And then from there, I went to Los Alamos National Laboratory and was involved in inertial fusion most of my career. Although I have actually studied neural nets as it relates to the chemical industry. And I also have done a lot of work in stockpile stewardship. So that's kind of a beginning background of my science. But let me tell you one other thing, just to give you a flavor of the kind of work that I was involved in. When I was doing solar physics, I was talking about AEU, huge distances, and tonight I'll be talking about light years. When I got involved in inertial fusion, I was talking about femtoseconds and picoseconds and nanoseconds. And so one of the things that I studied was an object that was only about 4 millimeters long, 3 millimeters in diameter. It was a cylinder, a hollow cylinder made of gold. Inside the cylinder was a sphere. The sphere, a lot of times, was hollow, filled with deuterium and tritium. You had laser light coming through the ends of that hull room, hitting the hull room walls, converting that laser energy to radiation. The radiation then actually imploded that sphere, and that sphere created neutrons and alpha particles. That program continues at Livermore with a facility called NIF and at the University of Rochester on a laser facility called the Magelssen. So that gives you a sense of my background, scientific background. I also have studied theology most of my life. I studied when I was, actually I've been studying since I was about 20. And about 12 years ago, 13 years ago, I took a 4-year course in theology. The course included Old Testament, New Testament, Christian history, and Christian theology. So that's the background of my religious background, my scientific background. Tonight, I'm going to start talking about the science. Okay, science related to the age of the universe, science related to the age of the Earth, of Mars, and of the Moon, of asteroids. What is the science behind that? And I'm going to be talking about the Big Bang Theory. All of you have probably heard of that. You know, what kind of science is behind people's ideas of the Big Bang? And I'm going to conclude by talking about the different, kind of, actually it's in this title, kind of the uniqueness of the physical laws. Why do I say unique? Well, I'll talk about that. We're in kind of a special universe. So, let's begin. Thanks, Judy. One of the first things you need to do to get an understanding of the age of the universe is determine distances. So I'm going to be talking about the size of the universe. And as I mentioned, I'm going to be talking about moon rocks, asteroids, Mars, and star clusters, and so on. So go ahead, Judy. Now, there are a lot of different techniques for measuring the distance to stars and galaxies. The simplest technique is called parallax. And so I have something for you to do. Take your finger. I'm going to point it on the coffee machine back there. Close your left eye. Focus on something. Okay, now open your left eye and close your right eye. Notice that the finger has moved far from the place where you first focused it. It's called parallax. Okay? Parallax is an accurate way of determining the distance to the closest stars. So Judy, the next view graph. This is an example of how parallax is used. In July, let's say you measure the location of a star, and then in January, you measure the location of that star again. There's an angle associated with that if that star is close enough. Now, there's always an angle associated with it, but if it's not close enough, the angle is so small that you can't resolve the distance. The angle is small enough so that if you take the tangent of the angle called d prime there, that's basically the distance from the sun to the earth divided by the distance of that star. And so, because that angle is small, it's just the angle. And so you know what the angle is, you know the distance to the star. And so that's how you begin to build up information about the stars that are closest to the earth. Now, that of course doesn't work for all the stars because the angle is too small. Recently, they have been able to extend the information from parallax by using the Hubble telescope. And from that, they can now measure distances out to about 10,000 light years. Judy, that's your graph. The next technique used that goes beyond that uses something called the color spectrum. This is the Hertzsprung-Russell diagram. Basically, it's luminosity versus temperature. The sun has a temperature a little over surface temperature, a little over 5,000 degrees, and you can see that there is kind of a line there. That line is called the main sequence, and if you look at the plot there, there are some stars that are a lot hotter than the sun, and some stars that are a lot cooler than the sun. Now, they create this Hertzsprung-Russell diagram using the parallax information, so they know what the distance of these stars are. Okay? So, with the reference stars, then you can begin to learn about stars that are much farther away. And how do they do that? Well, the sun, if you assume it's a black body radiator, do you know what black body radiation is? Some people do. Anyway, it is an equilibrium radiation. And if you get on the internet, you can quickly find pictures of what that looks like as a function of frequency. The sun has a very particular color spectrum. And I'll show you what a color spectrum is, but most of you know what a color spectrum is. How many of you have ever used a prism? Raise your hand. Okay. You looked at the light? You know, you've seen it in its different colors. Well, that's an example of a spectrum. Okay? The sun has a particular spectrum. Now, if you want to learn the distance to a more distant star, then if I use the sun as a reference, you could use any of those stars on the main sequence, but let's use the sun for the moment. Use the sun as a reference, and you look for a star which is far away that has that spectrum. Okay. With that spectrum, you know that that particular star emits like the sun. Now, how do you determine the distance? Well, give you another illustration. You're outside, it's night. You have light poles, and you're 20 feet from one light pole, and you're 100 feet from a different light pole. But you know from your past experience that the light from both of those light poles is the same. Okay? However, now that you're outside and you're looking at them, the one that's close to you looks brighter. And it looks brighter than the one that's far away. Well, it looks brighter because the radiation from that light is falling off like 1 over r squared. And so it's dimmer. But you can use that idea then to determine the distance from a star which is farther away. Because it's going to look dimmer than the sun, but it has the same spectrum. You know that it has the same surface temperature. And so you get an apparent brightness. And you also know how much that light has fallen off. It's a function of 1 over r squared. And you know the distance of the sun to the earth. That gives you the distance to that star. Okay. And so that's used to measure distances of 30 to 40,000 light years. Okay, still not a long ways away. The reason you can't use it beyond that is because all of you, well, many of you probably know that there's interstellar dust and other things in between the Earth and whatever star you're looking at, and that can change that spectrum. Not only that, it can eliminate some of the spectrum. And so there is a restriction on how far you can carry that measurement. So, next view graph, Judy. This doesn't really give you an accurate measurement, but it gives you a relative measurement. These are two galaxies seen from the Earth. And one, of course, looks much bigger than the other. And so you would infer there are very similar galaxies that one is much farther away. Next view graph. So, how do you measure distances that are really far away? Okay. Turns out there's a number of different ways of doing that. I'm just going to give you one. A supernova has a huge amount of radiation and can be brighter than a whole galaxy. And there is a measurement of supernova close to us. And from that measurement, and the fact that a particular supernova, supernova 1A, can then use that one that's close to us to measure a supernova which is very far away. Okay, because it's so bright you can see it. From that, you can actually make measurements that are 10 billion years. And so that's one of the techniques for getting the age of the universe. Is supernova. There's something called Cepheid variables where you can use some information about that, but I'm not going to talk about that tonight. And there are other ways. But this gives you a distance of, people estimate, about 13 billion light years. So how do you get age then? Well, you use the fact that the speed of light is constant. And all you do then, if the speed of light is constant and you have something that's about 13 billion years away, then it's 13 billion years old, okay? Because the light has reached you. It's taken that long. So that's how you begin to get an age for the universe itself. Next few graphs. Moon rocks. How many of you knew that the Apollo missions actually collected almost a ton of moon rocks? Anybody know that? Ah, a few people have. I was really surprised. So, there's been a lot of study of moon rocks. Probably the most accurate method that I'm aware of for measuring the age of the moon rocks and the earth rocks and other things that I'll talk about is something called radiometric dating. It's based on measuring the decay of an isotope of a particular material. And for moon rocks, one of those materials is uranium. Uranium-235 and uranium-238 both will decay in a certain period of time. And they actually decay at a different rate. And so you can actually get two different measurements using uranium. I'm not going to talk about uranium from now on. I'm going to be talking about potassium. Potassium-40 is a radioactive isotope, and it decays to argon-40. And now let me tell you, what is radiometric dating? Let me start by using one of the terms which is very common. It's called half-life. In this hand, I have 10 grams of potassium-40, okay? In this hand, I have 5 grams. The half-life is the time it took for those 10 grams to decay to 5 grams. And it's an exponential behavior, okay? And that's used to determine the age of rocks. Now, anybody have any idea what the half-life of that is for potassium-40 to argon-40?
Billion years.
Huh?
Billion years.
1.6 billion years, okay? And when I first saw that, I said, give me a break. How do you ever measure that? Well, good old internet. Get on the internet. There is a class where they actually show you how to measure that half-life. And it's very straightforward. What they used is potassium chloride, okay, and you know how much potassium-40 is in potassium chloride. It turns out it's 0.017%. You do a careful experiment. I mean, you can't, but it's straightforward. It's straightforward, special experiment, and you need a Geiger counter. Okay, that's it. And you can make that measurement. Anyone in this room, if you had a Geiger counter and some potassium chloride, and actually looked up that experiment, could do that experiment. And you get roughly 1.6 billion years for that particular half-life. So, next graph. I'm going to digress. I thought this was really fascinating. This is an event that occurred in Russia about 2 years ago. Any of you remember that? It was on the television? Yeah. When you saw that, one of the things that surprised me is there were a lot of people that got hurt. And I thought, that's kind of strange. I'm surprised that they got hurt. Because I didn't expect, it's bright. I didn't expect an explosion like that to hurt a lot of people. And I started thinking about it. What happens first when you have an explosion? You have a lot of light, right? That's the first thing you see is the light. And so you had people running to their windows to see what in the heck that was. Well, if you have an explosion, what else do you get?
Shock wave.
Yeah, you get a shock. Okay, so these people ran to their window, and the shock hit the window and smashed their windows and put glass in their face and their arms and everything. So people got hurt. So that's a lesson. Now, you see a really bright light, don't run to a window or anything like that. That was fascinating. Next view graph. Mars. How many of you have seen Martian? No. Okay. You know, doesn't that look like New Mexico? I was thinking, wow. Mars does look like New Mexico in many ways. So it happens that there's a paper that was published in 2013 by the rover, the Mars rover, where they did an experiment where they collected some rock called mudstone. Mudstone then was used to do a radiometric dating process. And the radiometric dating was potassium 40 to argon 40. Okay, so it's like what I've described to you, straightforward experiment. And what they found is that Martian rock was 3.6 to 4.1 billion years old. And they're getting numbers like 4.5 billion years for Earth rocks. Okay. And asteroids give numbers similar to that. Next, Judy. Polar ice caps. I had to show you that. They even have ice caps. So, that suggests, and there's some other things that you can do also, that the Earth, Mars, asteroids, the Moon, all on the order of 4 billion years, maybe a little bit older than that. Next view graph. This is another technique which is quite interesting. It turns out that star clusters can be of different types, and to get age of a really old star cluster, what you do is you look for a star cluster that has very few massive stars. By massive, I mean stars that are 5 to 10 times larger, more massive than the sun. Why? Stars that are more massive than the sun, by that amount or more, burn faster. And so they become depleted in a star cluster. So if you can find a star cluster which doesn't have massive stars, you're talking about an old star cluster. So what they'll do is they'll use a cluster close to the Earth that they know the distance to, and then find a star cluster which is like the one I just talked about, one that doesn't have any massive stars, to determine the age of that star cluster. Next view graph. Okay. So it appears that the Earth, or the universe, had a beginning. Carl Sagan never believed that the Earth had a beginning. Or not the Earth, but the universe. I thought that was really interesting. I remember listening to him. What happened? Well, one of the first things that happened I can describe by having you focus again on a simple experiment. Imagine a balloon that you're blowing up. A balloon that you've only blew up about a third of its size. You use a pen and locate a couple dots that are close to each other. And then you put another dot which is quite a bit farther away. Now you continue to blow up the balloon. What happens? The two dots that are close to each other, they move a little bit, not a lot. But the one that's far away has moved a lot. Okay? That's how they first realized the Earth, or the universe, was expanding. And what did they use? Next view graph. They used what's called the spectral redshift. Okay? Spectral redshift is a shift in the lines of the object. And it's a redshift, that means it's going away from you, and that gives you a velocity. So what they were seeing is that objects close enough were moving at one velocity, and things far from us were moving at a faster velocity. The other thing that you have to keep in mind here is that you notice that it's the whole spectrum. Okay? You can have part of the spectrum which looks like it's moved, but that's not enough. You need to have the whole spectrum to see the actual redshift. And so that was used to determine that in fact the universe is expanding. And so then people said, okay, if it's expanding, let's do the reverse. Let's collapse it back. And so they said, okay, it's collapsing back to a small object. So there had to be an explosion. And they said, okay, if there was an explosion, there should be evidence for an explosion. And one of the things that happens when something explodes is you get a lot of radiation. And if it's the beginning of the universe, this radiation can't be isolated over there, over here, or over there. It has to be everywhere. And so they started looking for this background radiation. And in the 1960s, they found it. Okay? It's cold, 2.7 degrees Kelvin. Okay? But it's everywhere. Okay? And it's uniform. So that suggests that there was an explosion. The third aspect of this is kind of interesting. If you had an explosion, people thought, okay, you know, you had a nuclear explosion like you would have in a star, and so what does that mean? Well, one of the things that was very puzzling to astrophysicists was that the abundance of helium was too high, much higher than they would expect just from the star formation. And so they did people did a calculation of this nuclear explosion. And what they found is that that nuclear explosion gave a helium abundance of about 24%, precisely what they see in the universe. So that's the three main areas that scientists use to talk about the Big Bang Theory. Go ahead, Judy. Okay. This is finely tuned universe. Well, the expansion rate. This is really curious. If the expansion rate was faster than we're seeing, then the gravitational force isn't strong enough to form stars. If it's slower, now I haven't done this calculation, I don't know where this came from exactly, but if it's slower than we have, you don't get stars either, you get mush. Now I don't know what mush means, but I assume what was done is that they did computer simulations of that kind of situation, and what they found is they didn't get star formation, you just got glob. So the expansion is just right. Gravity. If the gravity was stronger than it is, then what happens is the accretion process forms a star, but because gravity is so strong, it burns the nuclear fuel quite a bit faster. Calculations have done, with different gravitational constants, and that's exactly what they see. You basically burn up the stars. What happens if it's smaller? If it's smaller, those of you who have had background in hydrodynamics, thermodynamics, the accretion process is bringing matter in. Gravity's pulling things in. And what happens is that you need to have a collapse strong enough to start nuclear burn, because as you collapse that matter, you get a lot of thermal pressure and pressure pushing back. And so if the gravitational force is weaker, basically the system blows apart and you never start a nuclear reaction. So the gravitational force is just right for the star formation. Fundamental laws of physics. You know. Hopefully I'll get this right. I will say from the beginning that this is an area that is still not decided. There's some arguments. But I'm going to give you some arguments if you're interested in this area. I suggest that you look it up. Well, if the nuclear force is weaker, what happens is that the electromagnetic force then is too strong. And for example, you can't get the neutron to combine, or not the neutron, but you can't combine two protons to get helium, for example, and because of the electromagnetic force. And so the only thing you end up with is hydrogen. You don't have any heavy elements at that point. So we don't have our universe if that happens. If it's stronger, this is the area, there's not much argument about that, but this is the area there are arguments about. If it's stronger, you can actually get a diproton. That is, two protons will actually combine without a neutron. Okay, because they're able to overcome the electromagnetic force. And as a result of that, if that's a stable configuration, and that's where people argue, what happens is that you burn up all of your hydrogen and you end up with helium stars, which burn up very fast, and again, you don't have any universe like we see it, because all the stars have burned up. Now, there is an argument that says that the diproton is unstable, okay, and over a short period of time will separate. But the physics of what happens after that, they don't know. Because it involves a lot of particle physics and a lot of things they don't yet understand. So there isn't any idea of what that means, what happens, as far as I can tell, if that's a scenario. The nuclear reaction rates. This is an area that is also really quite fascinating. How many of you think carbon's important? Yeah. Yeah, we wouldn't live very long if we didn't have carbon, right? Well, there's an excited state that creates carbon, okay? And so we get a lot of carbon in the burn process. If that excited state also was there for oxygen, we would deplete our carbon and end up with oxygen, but not very much carbon. Well, it turns out there isn't that excited state for oxygen. And so you end up with a situation where we have a lot of carbon, and we have oxygen, but we have all the carbon for life on Earth. Otherwise, we wouldn't. The water molecule. Wow. The water molecule is incredible. It blocks out ultraviolet, X-rays, infrared. And I don't know if you're aware of it, but you know, those can be very destructive to the surface of the Earth. But it allows the light that we see, the light that's used for photosynthesis, for plant life. And so water molecules are very important for our existence. And so we have some pretty unique laws. Go ahead, Judy. So, I've talked about the age of the universe, you know, how we do that, how we measure that. I talked about the age of the Earth, Moon, Mars, so on. And I've talked about kind of the unique character of the physical laws. So, now I'm going to talk about something else. Go ahead, Judy. Keep going. I have some questions for you to think about. In our sessions, first of all, you can see that everything I've talked about so far is science. Okay, I'm talking about science. Now, how is faith involved in this? And I'll describe where these questions come from. Given the vastness of the universe, do I have an important role? Am I, we, significant or important? Where am I coming from? There is an argument that I hear that suggests, okay, the universe is huge. I'm a speck in the universe, doesn't make any difference what I do. I'm not important. Okay, that's where that question's coming from. In what way does the size and age of the universe make sense? I'll let you think about that. The Earth is in motion with its changing climate, volcanoes, earthquakes, floods. What is your perception of this motion? In what indirect ways does it impact our lives? I think this question comes from the following. Human beings really like to think that they're in control. And the question is, really? Are you really in control? What happens when you have a fire like we did in Los Alamos? I mean, you have to evacuate your home. What happens when you have a flood like they're having in Texas right now? You're in control? No, I don't think so. But it does more than that. I think that it probably hits you the strongest if you haven't had any calamities. Either at the death of a spouse or child, or when you're getting old and you face the end of life. And there may be other areas too, but certainly those areas really have an impact on most people. Stars are born through an accretion process, live for a while, become unstable, and eventually explode, spewing material into different parts of the universe. Does this evolution give us any insight into our own lives? Here, you know, haven't you ever wondered why there's a life-death cycle? You know, not only for human beings, but just about everything on Earth, everything you can think of. If you believe in God, what does the universe tell us about God? And if you don't believe in God, what does it tell you? And then the final one is mystery. As an older person, I find a lot of mystery in nature and in science, in many things that I'm involved in. And so, those are the questions. Those are things to be thinking about. You're really quiet. It's,
We're supposed to be thinking.
I am finished. So, any